We found that if n is 2 to the power k plus 1 is prime, then a primitive root existed. And we could find a primitive root by finding x that was not a solution to x to the power 2 to the power k minus 1 congruent to 1. But what if p is a prime but not of this form? Then in general, phi of p will be a product of prime powers. What can we do then? So remember, concrete doesn't hurt. Let's try a specific example. Let's say we're working with mod 37. So phi of 37 is going to be 2 squared times 3 squared. Can we find an element of order 2 squared? 4. So first, note that if x is a primitive root, so x to the 36 is congruent to 1 mod 37, then we can break up that exponent as x to the 9th to the 4th power. And since x is primitive, x to the 9th can't be congruent to 1. And it can't have order 2 since that would imply that x to the 18th is congruent to 1. So it must have order 4. Now it's useful to keep in mind a result is a result even if it's not what you're looking for. And this argument holds generally. If a is a primitive root mod n and phi of n is pq, then a to the power p has order q. In fact, we can go a little further because we didn't actually make use of the fact that this was phi of n, so this will hold for any composite order. If a has order pq mod n, then a to the power p has order q. So now the non-primitive roots mod 37 have to have order, and we'd like to find all elements of order which excludes any order that's a multiple of 4. So consider the congruence x to the 18th congruent to 1 mod 37. By Lagrange's theorem, there are at most 18 distinct solutions, but note that this congruence is going to be solved by all elements of the orders. Since there are 36 distinct values mod 37, this means there are going to be at least 18 values that are none of these orders, but the only remaining possible orders are 4, 12, and 36. And these correspond to elements of order 4. So if an element has order 36, I can rewrite that as where x to the 9th can't be congruent to 1. And if an element has order 12, we can rewrite that as where x to the 3rd can't be congruent to 1. So if x is not a solution to x to the 18th congruent to 1, then at least one of x, x cubed, or x to the 9th has order 4. A similar argument applies if we're trying to find an element of order 3 squared 9. As before, an element must have order. So if we strike all of the orders that include 9 as a factor, we'd like to find all elements of these orders, which would be included among the solutions to x to the 12 congruent to 1 mod 37. And again, since there are at most 12 solutions to this congruence, the remaining elements must be order 9, 18, or 36. And since 9 divides 18 and 36, then an element of order 18 or 36 corresponds to an element of order 9. Again, if that element has order 36, then y to the 4th has order 9. Or if the element has order 18, then y squared has order 9. So if y is not a solution to y to the 12th congruent to 1, then at least one of y, y squared, or y to the 4th has order 9. This means there must be an element of order 4 and an element of order 9, and as before, this means their product must have order 36. So let's try to find a primitive element mod 41. Since phi of 41 is 40, that's 2 cubed times 5, we want to find an element of order 8 and an element of order 5. The possible orders of an element mod 41 are, So we want to eliminate all elements of order, where we've struck out the orders that are multiples of 8. And we can do that with the congruence x to the power 20 congruent to 1 mod 41. And we find that 3 to the 20th is not congruent to 1 mod 41. So 3 does not have one of these orders. So it must have either order 8 or order 40. And if it has order 40, we're done, but it doesn't. And so we find that a equals 3 has order 8. Next, we want to eliminate all elements of order, which exclude anything that has an order that's a multiple of 5. And we can do this by finding solutions to y to the 8th congruent to 1 mod 41. And we find 2 to the 8th is not congruent to 1, so 2 must have order 5, 10, 20, or 40. So either 2 has order 40, order 20, order 10, or order 5. Now if 2 has order 40, then we can rewrite this, and so 2 to the 8th can't be congruent to 1. If 2 has order 20, then we can rewrite it as where 2 to the 4th is not congruent to 1. And if 2 has order 10, we can rewrite it where 2 squared can't be congruent to 1. So 1 of 2, 2 squared, 2 to the 4th, or 2 to the 8th has order 5. And we find that 2 to the 4th has order 5. So 2 to the 4th, that's 16, has order 5. And so we have an element of order 8. We have an element of order 5. So their product, 48, is going to have order 40. Or, since 48 is congruent to 7 mod 41, then 7 is a primitive root.